Parachute is deployed. We are decelerating. Teachel has separated. We're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for backshell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started. Touchdown confirmed. We're safe on Mars.
We had a major success when we deployed the arm for the first time on Mars. This is critical to ensuring that we can get sample into our instruments and use the arm for its scientific purposes. The ChemCam unit, or chemistry and camera instrument, fired the laser for the first time on Mars, using the beam from the science instrument to interrogate a fist-sized rock called Coronation. Before we could drive Curiosity, we wanted to wiggle our toes a bit and test the steering actuators. This is the first time we moved the wheels on Mars. We hit a major milestone on Mars. We completed our first drive of the Curiosity rover. We drove approximately 3 meters forward and performed 2 60-degree rotations in the clockwise direction, with imaging in between. We then drove backwards just under 3 meters in order to test the wheels in the opposite direction. This put us in a great configuration to make observations of the scours left by the descent stage engines. We've got a very interesting science experiment coming up here on Mars. We are turning on the sample analysis at Mars instrument for the first time to do an atmospheric experiment. This is where we let in atmosphere into the instrument and perform various science experiments to determine the composition of the atmosphere. This is the first time that this is happening. Within days, we will start our journey to our first chosen destination on Mars, Glen Ellig. We hope to obtain our first drilled rock sample on Mars at this location. The team named the landing site this week after the famous science fiction author Ray Bradbury on his birthday, August 22nd, and he would have been 92.
Curiosity is still heading to Glen Ellig. We've just stopped at the Bathurst Rock Formation to check it out with the robotic arm-mounted instruments, a hand lens imager and a spectrometer. Got some great science data there for the science team. And now we're moving to a new location called Rocknest. And we've come to Rocknest because it has nice wind-blown sand drifts. At the Rocknest location, we really are entering a new phase in Mars exploration with Curiosity. We're starting the surface sampling part of the mission. The reason this is a 1-ton rover with a 200-pound robotic arm is because we have these tools to acquire bits of Mars, either with a scoop or with a drill, process those samples for our very sensitive analytical lab instruments. So our scoop, this is not a giant backhoe on Mars. We basically have more like an oversized tablespoon attached to the end of the arm, and we grab on the order of 20 grams of material, and we position the arm over the soil target, and then we just actuate the scoop, do a little bit of vibration to kind of level out the sample, and then raise the arm up, close the scoop, and carry on with our sampling activity.
When we first arrived at Rocknest, we performed a wheel scuff maneuver. This is our rover's version of kicking up the dirt with your hiking boot to determine if the Rocknest area was indeed a good first scoop target. The first scoop was successfully performed on Sol 61, and the entire team was excited to see the Mastcam images showing the scoop full of dirt, as well as the video of the vibration activities performed with the turret-mounted tools. This vibration allows the team to level out and remove any excess sample before closing the scoop, and and it also provides some insight into the makeup of the soil. Any large particles would tend to float up to the top as the entire sample is vibrated, much the same way you would shake out the marshmallows in your box of Lucky Charms. Curiosity processed the scoop sample through Chimera, our labyrinth of passageways at the end of the arm that we use to sieve and portion the soil sample. We did some internal sandblasting by vibrating the sample at different orientations of the turret in order to remove any internal contamination.
A soil sample was dropped off to the rover's observation tray for assessment by the science team. This sample was determined to be suitable for drop-off to the CheMin instrument. The CheMin instrument uses X-rays in order to image the sample and determine what minerals make it up. This helps geologists understand how the rock formed and how it's related to other rocks we've studied so far on Mars. Scientists identified numerous bright grains in the soil because of the small piece of plastic from the landing event that had been found earlier in the week. The team proceeded cautiously, dumping the second scoop collected and imaging the bright grains. These bright grains were later determined to be components of the Martian soil, and therefore the sample was deemed to be suitable for delivery to the CheMin instrument for analysis. The science team requested Mastcam and Navcam mosaics of the outcrops in the direction of Glen Elk to plan Curiosity's journey to this next science destination.
In its spare time, Curiosity has also been making measurements with other instruments, including the ChemCam instrument, which is what I work on. ChemCam is actually two instruments in one. It includes a camera with a telephoto lens, and it also has a laser that vaporizes a very small amount of rock so that we can tell what its chemical composition is. We've been analyzing rocks in an area called Rocknest, and I'll tell you in particular about one called Zephyr. This one is interesting because it appears to be made of two different types of materials. It's got this harder, more resistant material on the top, capping it, and then beneath that it has a lighter colored, softer material that appears to erode more easily. It's actually eroded into a set of natural arches, so some of our team members have taken to calling it Stonehenge. This feature is really only an inch long. We're shooting this from about 8 feet away, making the pointing very difficult. So that's why we decided to do 9 points instead of just 2, just to make sure we would hit the material of interest. Coming up, we'll be able to use this information that we've learned from ChemCam in order to decide which targets we should hit next with other instruments.
ChemCam performs what we call X-ray diffraction measurements on powdered rocks and soil samples. And X-ray diffraction is the best method for telling us what minerals are present in a rock or soil because it's sensitive to the arrangement of atoms and minerals. As the X-rays strike the soil sample, ChemCam shows us how mineral crystals distinctively interact with X-rays, and this image shows our first X-ray diffraction results. The diffraction signals appear on the detector as rings that represent the fingerprint of the individual minerals. The rings tell us not only what minerals are present in the soil, but also how abundant they are. The ChemCam data provide us with distinctive signatures of the minerals plagioclase feldspar, pyroxenes, and olivines. Peridot is a variety of olivine. Just keep in mind that the olivine in the soil sample is much smaller than these crystals. Roughly half of the soil consists of poorly crystalline material such as volcanic glass. Thus, the Martian soil appears very similar to some weathered basaltic soils that we see on Earth in places like the flanks of Mauna Kea, Hawaii. You can appreciate how revolutionary ChemCam is when you consider that instruments of this type on Earth are typically about the size of a double-wide refrigerator, and the ChemCam instrument on the Mars Science Laboratory is about the size of a shoebox. ChemCam has been modified for use on Earth in places such as Antarctica and the Arctic. It's also been applied for the detection of counterfeit pharmaceuticals around the world, and a modification of the instrument has been used in archaeological studies to help us understand the nature of the surfaces and how we might protect them. In the coming weeks and months, we're excited to measure more X-ray diffraction data on soils and rocks to tell us much more about the geology of Gale Crater.
While our robotic explorer has been busy characterizing the surface of Mars, the SAM team has also been busy, but we've been looking at something invisible, the Martian atmosphere. SAM, or Sample Analysis at Mars, is not one instrument, but 3, all of which are designed to work together to chemically characterize Mars. SAM measures chemical elements and molecules in a mass or size range between 2 and 535 mass units, and we do this by looking at gases. We can bake solid samples until they give up their volatile components or their gases, Or we can directly inhale the Martian atmosphere through our inlet ports. With our QMS, SAM is able to detect the most dominant gas in the Martian atmosphere, carbon dioxide. We've not only measured its abundance in the ratio to other gases in the Martian atmosphere, but we've also measured its isotopic character. The other instruments are a tunable laser spectrometer and a gas chromatograph, the latter being used mostly to look for organic molecules in solids. Now, the tunable laser spectrometer has a special role for SAM in that it can very sensitively detect the organic molecule methane, which has been observed from the Earth telescopically and also by the Mars Express orbiter at very, very low limits in the Martian atmosphere. We're trying to discover whether or not we can see this molecule from the Martian surface and if it has any variation from season to season. In the coming months, wherever Curiosity goes, SAM will continue to sniff the Martian atmosphere, periodically looking for changes on a seasonal, maybe even diurnal basis, and that will tell us something about the dynamics of the exchange between the surface and the atmosphere.
A lot of what this mission is about is figuring out the possibility that ancient Mars was a habitable environment. But we're also studying the present environment. Two instruments that help with that are the RAD instrument and the REMS instrument. The RAD instrument is a radiation assessment detector. It measures the high energy radiation coming in from the cosmic rays and the sun. That radiation is changed as it goes through Mars' atmosphere to where we detect it on the surface. These measurements are helping to understand what the environment's like on the surface so that future astronauts will know how they can protect themselves from this harmful radiation. Another instrument that Curiosity has that measures the modern environment is called the Rover Environmental Monitoring Station. It's basically our weather station. We measure a lot of things, including pressure and humidity, temperature, and wind. It's been seeing little dips in pressure around noon that seem like the signature of dust devils. Only thing is, our pictures haven't turned up any dust devils. Spirit and Opportunity saw lots of dust devils moving across the horizon. Our best guess at what's going on is that Curiosity is seeing dust devils go right over it. So what we think is happening is the same sorts of vortices driven by convection are occurring on Mars at Curiosity's site, but just not picking up dust. Another thing that REMS has been measuring is winds. Turns out we're in a pretty interesting place inside of Gale Crater. We're right at the base of a 5-kilometer high mountain to the south of us, and then there's a pretty tall crater rim to the north of us. And we're sitting kind of in a flat depression between the two. The winds blow up and down the mountain as the temperature changes during the day, and up and down the crater slopes, and then along the depression where we're at. So right now we're trying to figure out from the REMS data exactly which parts of that wind field we're measuring.
After several weeks of being stationary at the Rocknest site, we began driving again on SAW 100. This marked a significant milestone on the mission as we reached about a half a kilometer of total driving distance on the surface of Mars. The left front wheel is sitting on a rock that we've dubbed Bell Island. We plan to back up off that rock to bring the rock into the ARMS workspace, and we're going to do some contact science on it with APXS and MAHLI. After completing our science campaign at our current location, we're going to be moving to the east to a place called Point Lake. From here, we're going to be looking for a target to perform our first ever drill on Mars.
We've wrapped up our scientific study of Rocknest, which also means that we've completed the checkout and first scientific use of all of our instruments on the rover, and it truly is working great. We began the Rocknest campaign by searching for a suitable drift of sandy soil using our Mastcam color cameras. We used our ChemCam laser and our APXS chemical sensor to do an initial chemical analysis of the soil, determining whether it was similar to soils that we understand from Spirit and Opportunity, and therefore safe for scooping and sending to our laboratories. We used MAHLI, our hand lens imager, to take close-up views of the soil to look at different particle sizes, shapes, and colors, and how they change with depth. We then scooped up the soil and analyzed it with our X-ray diffraction instrument that can identify minerals in the soil based on their unique crystal structure. But it turned out that a good amount of the material in the soil was not crystalline, but that's no problem for our other laboratory, SAM. SAM heated up the soil in an oven and measured various gases released as the soil components broke down, such as water, carbon dioxide, oxygen, and sulfur. Not surprisingly, the results show a composition that is typical of Mars soils studied at other sites, with perhaps some very simple carbon-containing molecules and perchlorate salts. We haven't yet seen any complex organic molecules, but sand isn't the best place to look. Finally, it's worth remembering that the big questions in science, whether Copernicus finding that the Earth goes around the sun, or Darwin showing that natural selection drives biological evolution, were answered only after many measurements were taken, compared against one another, and hypotheses were proposed and tested against the data. Only then can the big picture emerge and the theory get accepted. It'll be no different for Curiosity in its mission to understand the habitability of ancient Mars at Gale Crater. There won't be any single image or measurement that'll answer everything. We're in it for the long haul. But now we know that we have a fantastic rover, a great set of tools, and a fully functional scientific payload. So let's get on exploring.